Hello viewers, welcome to this next lecture on the NPTEL MOOC course on Mathematical Portfolio Theory. From today's class, we will begin a new topic, and that is on risk management in case of portfolio theory. And so far you will recall that in the Markowitz framework, we have talked about the variance or equivalently the standard deviation as the measure of risk. And in this part of the course, we will introduce a couple of more risk measures, namely value at risk and the conditional value at risk. So accordingly, we begin this lecture today by talking about mostly about quantiles, and then that will be used to define what is going to be the value at risk, and we will look at some of its properties and identify some of the shortcomings of value at risk, and then that would motivate our moving to the next topic, namely the conditional value at risk. So, let us begin today's lecture by starting to talk about what are quantiles. So, first of all, we start off with the definition of what are quantiles. So, let x be the discounted gain of an investment. So, we consider an investment and we consider its discounted gain, and we begin with the following observation that the value at risk, which we will define later on, or abbreviated as VAR. So, in this case the R is capital, unlike the small r in case of variance. So, this is closely related to the values of the distribution function. So, recall that we had defined what is the distribution function in the first week of the course, and this distribution function was given by capital F subscript x of the random variable x, and also what are known as quantiles. So, quantiles will be defined in terms of f x. So, let us begin with an example on distribution function. So, what you do is now we go back to the binomial model and consider the following binomial model. Suppose that the initial stock price is 100, and then it can go either up to 110 or come down to 90 at time 1, and from 110 it can go up to 121 or come down to 99, and from 90 it can either go up to 99 or come down to 81. So, that means the up factor is 10% and the down factor is also 10%. Now, the probability of going up is taken to be 0.8. So, this is of probability of going up, and consequently 1 minus p is 0.2, and that is the probability of going down. So, neglecting or ignoring the time value of money, this is just for the purpose of simplicity and for illustrative purposes. The discounted gain after the second step is given by x equal to s of 2 minus s of 0. So, normally your discounted gain would be something like the discounted value of e raised to minus r t into s of t minus s 0. But here I am saying that that r is equal to 0%. So, consequently I am taking my x to be s of t minus s 0, where my t is going to be equal to 2. So, now you observe carefully that this value of s of 2 has 3 candidates. What are those candidates? This is either 121 or 99 or 81. and S0 of course is deterministic, and that is equal to 100. So, therefore, x can take 3 values. What are those 3 values? It is going to be 121 minus 100, that is 21, 99 minus 100, that is minus 1, and 81 minus 100, that is minus 19. Now, this value of 121 is a result of the stock price reaching 121 at the time t equal to 2. So, this will happen as a result of 2 upward movements with probability p followed by probability p. So, this x value of 21 can happen with probability of p square is equal to 0.64. Remember that p is equal to 0.8. Now, this value of minus 1 is a result of you reaching amount of 99 at time t equal to 2, and this can happen either as a result of an upward followed by downward movement with probability of p into 1 minus p, or as a result of downward movement followed by an upward movement with probability of 1 minus p into p. So, the probability of reaching 99, this is going to be equal to 2 into p into 1 minus p. And remember, p is 0.8 and 1 minus p is 0.2. So, this becomes 0.32. And finally, you arrive at the value minus 19 in the situation where S of 2 is equal to 81. So, in this case, what is going to be the probability? So, it is a result of 2 consecutive downward movements. So, the consecutive or the concurrent probability is going to be 1 minus p square equal to 0.04. Okay, now what you are interested in is in the context of discussing value at risk, we first need to talk about quantiles, and before we start quantiles, we need to talk about what is the distribution function. So, accordingly, we now consider the distribution function f(x) of this x. So, how is the distribution function going to look like graphically? So, this is the distribution function, and I want to look at it from a graphical point of view. So, on the x axis I have x, and on the y axis I have f of x, and remember the maximum value of f(x) is 1, and the values of x that are allowed are 21, minus 1 and minus 19. So, minus 19 will be somewhere here, minus 1 will be here, and 21 is going to be here. So, the probability of a value being less than minus 19 is 0. The f(x) is going to be 0 here. Now, at 19 the probability is 0.04. So, this is 0.04 this height, and this is the probability from minus 19 to minus 1. Now, at minus 1 the cumulative probability is going to be 0.04 plus 0.32. So, that is going to be 0.36. So, it is going to be 0.36, and this is the probability at 1, and this is the probability that will last till 21. And when you reach 21, then the total probability is going to be 1. So, the graph will look something like this. So, this means that from 0 to less than up to less than minus 19 the cumulative probability is 0. From minus 19 but less than minus 1 the cumulative probability is 0.04. From minus 1 but less than 21 the cumulative probability is 0.36, and from 21 onwards the cumulative probability is going to be equal to 1. So, for example, the probability that the investment will, so this is for example, the probability that the investment will lead to a loss of L, and what is loss? Loss is negative of gain, so that is minus x less than 19. So, I want to find out what is the probability that the loss will be less than 19. So, this is nothing but the probability of L being less than 19 is the same as probability of x being greater than minus 19, and this is nothing but 1 minus probability So, using the complement property of probability, this is 1 minus probability x less than or equal to minus 19. What is the probability that x is less than or equal to minus 19? This is nothing but 1 minus probability that x equal to minus 19, which is 0.04. And so, 1 minus 0.04 is 0.96. So, this means that 95% chances are that the loss will not be more than 19, and there is only a 4% chance that the loss is going to be more than 19. So, I can say that. So, from here this means that with likelihood of 96%, we will lose no more than an amount of 1. All right. So, for example, if we agree to ignore the worst 5% of the potential outcomes, our worst scenario would be loss of 1. But if we are willing to exclude the worst 2.5%, then the loss of 19 also has to be taken into account. Okay, so let us just recall the following, that if your say omega f p be a probability space. So, here omega is the sample space, f is the sigma algebra, and p is the probability measure. So, this ordered triplet is a probability space, and x from omega to r is a random variable. You recall that the cumulative distribution function CDF is nothing but a function f x on r to 0 1. Remember, f x can only be between 0 and 1, and this is defined by f x of x is equal to probability of x less than or equal to x. And you recall that this is right continuous and non decreasing. Okay, so now that we have brought the definition of a distribution in case of a random variable, and more specifically we talked about the cumulative distribution function, and we looked at an example in the context of our application in finance, namely what is going to be the discounted gain. It is now time for us to move into quantiles, which, as I had mentioned earlier, is the prerequisite or the prelude to the definition of value at risk. So, now accordingly we start off with the definition of quantiles. So, the quantile says the following, that for alpha belonging to 0 1, so any value of alpha lying strictly between 0 and 1, the number, and I will define a couple of numbers. So, there is a number which are denoted by q subscript alpha of x, which is the infimum of x, that is the smallest x, such that alpha is less than the f x of x, or the cumulative distribution function of x, and this is called the upper alpha quantile. Remember, alpha here is pre-specified, of the random variable x. And motivated by the same this setup, we now say that, so now we have talked about a upper alpha quantile. So, then we can now accordingly define the lower alpha quantile, and then this number q subscript alpha is going to be the infimum of x such that alpha. So, remember here alpha was strictly less than the CDF, and here I will take alpha to be less than or is equal to the CDF of x, and this case we call the q alpha of x, q subscript alpha of x is called the lower alpha quantile of x. So, to reconcile this upper and lower quantile, we make the observation that any q which lies in the closed interval of the lower quantile and the upper quantile, this is called an alpha quantile. So, the next thing that we do is we now look at the interpretation of the quantiles in a graphical manner. So, we take the x on the x axis and the CDF or fxx in the y axis, and remember that the maximum value for this is going to be 1. So, let us now fix our alpha. In both the cases, but we consider two different distributions. So, this is the first distribution, and this is the second distribution. So, in this case you observe that this point that I have here, this point is both the lower as well as the upper quantile. Now, why do I say that both of them are the same point, both the upper and the lower quantile? So, if you look at the lower quantile definition, the lower quantile definition says that we will take the smallest x such that alpha is less than or equal to fx of x. So, the region of alpha which satisfy alpha is less than or equal to fx of x, it is going to be this region which is above this line. So, alpha less than or equal to x, if you look at all the values of x such that alpha is less than or equal to x, the smallest of that x value is this, and likewise if you look at those values such that alpha is strictly less than fx of x, again the smallest value of x is this. So, as a result you have the lower quantile being the same as the upper quantile, and so here this q is just going to be a single point, because this interval reduces to a single point. However, in the second case if you observe carefully, we have a distribution, the graph lying in a coincidental manner at alpha. So, if you in this case this particular point here let us now look at the second case. So, here this particular point, this is going to be the lower quantile and this point is going to be the upper quantile. And the reason for this is the following, that for the lower quantile you need alpha less than or equal to fx of x. So, here on this line the alpha is going to be equal to fx of x. In the previous case, alpha less than or equal to fx involved this line, but here since alpha is coinciding with fx of x, so we have to consider this line when we are looking at the lower quantile, and so accordingly the smallest value of x for this part is going to be the q alpha of x. However, the region for the upper quantile, the region which I have to consider is alpha less than fx of x. So, accordingly I have to consider that part of the distribution which lies here, and the smallest value of x which satisfies the region of alpha strictly less than x is going to be q alpha of x. So, here the lower and the upper quantiles coincide, but here the lower and the upper quantile are distinct from each other. And the primary reason why this has happened is that because the CDF graph coincides with the value of alpha in the second case, but not in case of the first one. So, if you go back to the example, you can verify for yourself the example that you had done for f x of x. So, if your alpha you take 3 different values, that is alpha is 0.025, alpha is 0.04 and alpha equal to 0.1, then the lower quantile is going to be minus 19 and minus 1, and the upper quantile is going to be minus 19, minus 1 and minus 1. So, you observe carefully that amongst the 3 values of alpha, the only scenario where the CDF matches alpha is going to be 0.04. So, in the other cases these 2 quantiles are identical, but in this case because it coincides with the f x values. So, in this case the lower quantile q alpha of x, this is going to be strictly less than the upper quantile q superscript alpha of x. Okay, so, now let us do a proposition, and the proposition states the following, that if you let x and y be random variables, then I state 4 results. So, the first one is, if your x is greater than or equal to y, this implies that q alpha of x, that is the upper quantile of x, is greater than or equal to upper quantile of y. The second result is that for any real number b, the upper quantile of x plus b is going to be upper quantile of x plus b. The third result is that for a positive b, the upper quantile of Bx is b into upper quantile of x, and finally, and this is a very crucial result, that the upper quantile of minus x of alpha, the upper quantile alpha of minus x, this is going to be minus q of lower quantile with respect to 1 minus alpha. So, let us start doing the proof of this. So, the first proof is that, so what is the assumption in the first result, that your x greater than or equal to y implies that this quantile relation holds. So, if your x greater than or equal to y, then in order to prove this result, I will need to make use of the CDF. So, f x of x, by definition, this is probability that x is less than or equal to x, and this probability is going to be less than or equal to probability of y less than or equal to x, which is f y of x. And the reason is the following, that if you have your x less than or equal to x, then automatically your y. So, if you have x less than or equal to x, this will automatically imply that y less than or equal to x. So, that means the probability of this happening, which is given here, must be greater than or equal to the probability of x being less than or equal to x, which is here, and this is probability of x less than or equal to x is by definition f x of x, and probability of y less than or equal to x is by definition f y of x. So, from this relation involving this and this term, what you can say is that, so therefore, so for upper quantile we need alpha strictly less than f x of x. So, if your alpha is strictly less than f x of x, then obviously it will mean that since your f x of x is less than or equal to y, so it obviously implies that alpha is less than f y of x. So, this means that if your alpha is less than f x of x, it means that alpha is less than f y of x. So, that means that all the values of x which satisfy alpha less than f x of x must also satisfy alpha less than f y of x, and maybe there are other values of x which satisfy this condition. So, hence what do you have? All those values of x such that alpha is less than f x of x, the set of all such x, that must be a subset of all those x such that alpha less than fy of x. Now, since all the values of x on for fx of x is a subset of all the values of x such that for fy of x. So, therefore, what will you have? You will have the smallest, since this contains more number of x. So, that means that the infimum of all those x such that alpha is less than fx of x, the smallest x satisfying this condition obviously must be greater than or equal to the smallest x which satisfies this condition, that is infimum of x such that alpha less than fy of x, right, simply because this contains more values of x. So, it might actually have a smaller value of x that is not present in this set. Now, what is infimum of x such that alpha strictly less than fx of x? This by definition is q alpha of x, and infimum of x such that alpha strictly less than fy of x. This by definition is the upper quantile of y. So, what do you get? So, you basically get q alpha of x, the upper quantile of x is greater than or equal to the upper quantile of y, which is this result. Okay. Let us come to the second result now. So, for the second result, we consider that f of x plus b of x. So, I look at the cumulative distribution of x plus b. This by definition is probability that the random variable x plus b is less than or equal to little x plus b, and if we cancel the b's on both the sides. So, this will become probability x less than or equal to x, and this is fx of x. So, now we are in a position to prove that q alpha of x plus b, the upper quantile of x plus b, what is this? This is by definition infimum of all those x plus b such that alpha is strictly less than f of x plus b of x plus b, and I can, since b is a constant, I can take this outside. So, this is going to be infimum of all those x such that alpha less than f of x plus b of x plus b plus the b which goes outside, and this from this result that we have obtained here, I can replace f of x plus b to obtain infimum of x such that alpha is less than fx of x plus b, and this infimum by definition is the upper quantile of x plus b. So, let us now come to the third result, which is the upper quantile of bx where b is positive. So, for this again we considered the distribution function or CDF of f of bx of x. So, this by definition is probability of bx less than or equal to x, and this is nothing but probability of x being less than or equal to little x over b, and this by definition is going to be fx of x over b, that is the CDF of x over b. So, hence for b greater than 0, the upper quantile of bx is going to be infimum of those x such that alpha less than f bx of x. So, this is by the definition of upper quantile, and this is infimum of those x such that alpha less than fx of x by b, making use of the result stated in the beginning. And this can be rewritten as infimum of, I can write the little x as b into x over b such that alpha less than fx of x over b. Now, since b is a constant that is positive and we are taking the infimum, so the b can come out, and if I take my x over b to be equal to some y, so this expression now becomes, with the b outside, it becomes infimum of all those y's such that fx such that alpha is strictly less than fx of y, and this infimum by definition is nothing but the upper quantile of x, since we are considering alpha less than fx of y. Okay, so, this proves the third result, and now we focus on the fourth result, that is q alpha of minus x is minus q of subscript 1 minus alpha of x. So, it is connecting the upper quantile of alpha with the lower quantile 1 minus alpha. So, this proof goes in a couple of steps. So, the first step would be what we do is that we show that for any real number b, infimum of x such that b is less than or equal to probability of x strictly less than x, this must be greater than or equal to infimum of x for such that b is less than or equal to probability of x no longer strictly less than x, but less than or equal to little x. Okay. So, now probability of x being less than x is obviously less than or equal to probability of x less than or equal to x, because here we obviously have also included the event that x is equal to x. So, obviously, this probability is going to be greater than or equal to the probability of capital X being strictly less than x. Now, if b is less than or equal to probability of x strictly less than x, right. So, that means I am looking at this condition, then from here obviously we get that b is less than or equal to probability of x less than or equal to x. So, now that this implies this, so therefore, all those values of x such that b is less than or equal to this condition, that is probability x strictly less than x, this will be a subset of all those x such that this condition hold, that is b is less than or equal to probability of x less than or equal to x. And hence, if I take the infimum, so obviously this right hand side contains more values of x. So, it is likely that the infimum of this might be a value of x that is not contained here. So, accordingly the infimum of x such that b less than or equal to probability is x strictly less than x, this infimum might be smaller. So, this is going to be greater than. So, this is pretty much on the same lines as the proof for part 1. So, this infimum is going to be greater than or equal to infimum of x such that b is less than or equal to probability of x less than or equal to x. Now, in step 2 we do the following. In step 2 we rule out the possibility that the inequality in step 1, that is this inequality, is strict. That means, this is a strict inequality. So, we have to rule out the possibility that this is a strict inequality. Now, let us start off with contradiction and suppose that, so you will use the approach of contradiction and begin with the assumption that the strict inequality holds. Suppose that the strict inequality holds. So, this means that this is strictly greater than the term on the right hand side. Okay. So, this means that my assumption is that the infimum x such that b less than or equal to probability of x strictly less than x, that is this expression on the LHS, is strictly greater than this expression on the RHS. So, that is infimum of x such that b less than or equal to probability of x less than or equal to x. Now, if the strict inequality holds, then between these two numbers, remember these are just real numbers. So, between these two real numbers another real number will exist. So, this means that there will be an x star sandwich between them two, and this x star would be some real numbers, because between any two real numbers there is another real number. Now, when we say this x star, we consider that this x star satisfies this property, then what do we have? So, then we will have probability that x is strictly less than x star is less than b. So, please remember that this x star is less than the smallest value of x which satisfies this condition. So, that means that obviously since this x star is less than the smallest value which satisfies the condition that b is less than or equal to probability of x less than x star. So, this means that this x star will not satisfy the condition that b is less than or equal to probability of x less than x. So, that means that this means it will satisfy the condition that b is greater than probability of x less than x, little x being equal to x star. Now, since the function x that is this probability of x less than x as a function of little x is left continuous. So, we can find an x hat, a real number x hat such that it lies between this quantity and this quantity. So, this means that infimum of all those x such that b is less than or equal to probability x less than or equal to x is strictly less than x hat, strictly less than x star, for which probability of x less than x hat is less than b. Now, since x hat is greater than, so since this x hat is greater than infimum of the x's satisfying this condition, so it is greater than the infimum of all those x such that b is less than or equal to this condition, that is b is less than or equal to probability x less than or equal to x, we have that b is less than or equal to probability of x less than or equal to x hat. Right. So, here you see all the smallest value of x is such that this condition is satisfied. So, obviously, you will have b being less than or equal to probability of x less than x hat, and this is a contradiction. Contradiction to what? So, basically from the previous step, that is looking at the region of x star. So, from the previous step applicable to this part, we got that probability x less than x hat is less than b, and we have got probability x less than or equal to x hat greater than or equal to b. So, therefore, we have arrived at a contradiction. Okay, so, now that we have this result that these two are equal, so the strict inequality does not hold in this relation, we can now make use of this to prove our main result. So, to prove result 4, so now to prove result 4, we shall use the fact that f of minus x of x, this by definition, what is this going to be? This is going to be probability of the random variable minus x being less than or equal to x, and this is equivalently probability of the random variable x being greater than or equal to minus x, and this is nothing but 1 minus probability of x being strictly less than minus x. So, therefore, the upper quantile of minus x, what is this going to be? This is going to be the infimum, by definition is going to be the smallest value of x such that alpha less than f of minus x into x. And what is this? The infimum. So, this is by definition of our quantile, and this can be written as minus supremum of minus x such that alpha is less than f of minus x x. So, it is like the infimum of a variable is going to be minus supremum of the negative of that variable. Now, what can I rewrite this as? Now, let us focus on this term. So, this can be written as minus supremum of minus x such that alpha is less than. So, remember this alpha is less than f minus x of x, see this condition, that is same as alpha being less than this condition. So, I can write this as alpha being less than 1 minus probability of the random variable x being strictly less than minus x. and this can be rewritten as minus supremum of y such that alpha is less than 1 minus probability of x less than y, where y is equal to minus x. So, this can now be written as minus supremum of y such that probability of x strictly less than y is less than 1 minus alpha. So, I am just moving this to the left hand side and alpha to the right hand side. So, this can be now rewritten as minus infimum of y such that 1 minus alpha. So, the complement of this is going to be 1 minus alpha less than or equal to probability of x strictly less than y. So, supremum of those y's which satisfies this condition is simply going to be the infimum of y which satisfies the complement of that condition. And the reason you can do this is that the function y to probability of x less than y is non-decreasing. And this can now be written as minus infimum of y such that 1 minus alpha less than or equal to p of x strictly less than y. What is this? This is nothing but f x of y. And observe carefully, this is y given that 1 minus alpha less than or equal to f x of y. So, since 1 minus alpha is less than or equal to f x of y, so this is going to be nothing but the quantile of x, and since there is a less than or equal to sign, this is going to be the lower quantile of 1 minus alpha. So, this entire expression is now this lower quantile 1 minus alpha of x, and of course, we have the negative sign. So, hence it proves that. So, therefore, from starting from here we have arrived here. So, you get q alpha of minus x, there is the upper quantile of minus x is nothing but the lower quantile 1 minus alpha of x with a negative sign. So, this proves the fourth result. So, we conclude with a couple of lemmas. The first lemma, so this is let me call this lemma 1 for today. So, it says that if your f x is continuous and strictly increasing, then the upper quantile of this x is simply going to be f x inverse the inverse of the CDF of alpha. So, how do you get the proof of this? So, what is the given condition? The given condition is that f x is continuous and strictly increasing. So, I can say that the given condition for f x, the CDF, this ensures that it is invertible, because I will need to have the inverse of f x. Also, it ensures that the inverse function, since it is invertible and the inverse function f x inverse exists, and this inverse function f x inverse alpha is also continuous, and most importantly, since we are talking about upper quantile, so that the condition that is required for alpha quantile, that is alpha strictly less than f x, this condition is equivalent to the condition that f x inverse of alpha is strictly less than x. So, based on this condition that f x is continuous and strictly increasing, we have that it is invertible, the inverse function is continuous, and most importantly alpha strictly less than f x of x is equivalent to this relation. So, what does this give? So, this gives that the upper quantile of x, which is by definition infimum of all those x, such that alpha strictly less than f x of x. What is this going to be? It is going to be infimum of those x with an equivalent condition of alpha strictly less than f x of x, which is this condition. So, it is the smallest x such that f x inverse alpha is strictly less than x. And since f x inverse is continuous, so the smallest value of x that this condition is satisfied is nothing but f x inverse of alpha itself. Okay, so this is a very crucial result, that is lemma 1, and now we state lemma 2 without proof, and it says the following, that let x be a random variable. Now, if your f from R to R, that is a real valued function on R, is right continuous and non decreasing, then the following condition hold, that the upper quantile, so remember that if your x is a random variable, then obviously, and f is a real valued function which is right continuous and non decreasing, then f of x is also a random variable, and this upper quantile of f of x becomes equal to f of the upper quantile of x. So, that means this quantile and this f interchange their position for this random variable x and this function f. And remember that for most part we will be looking at x to be the specific random variable of the discounted gain on a asset. So, this brings us to the end of this lecture. Just to do a brief recap of whatever we have done in this lecture, we started off with recognizing the fact that the only risk measure that we have done so far is the standard deviation or variance that we have seen in case of the Markowitz framework. And then we decided that we need to move on to something more robust, and accordingly we will consider two different risk measures, namely var and c var, which is the value at risk and the conditional value at risk. And in order to motivate the definition of var and consequently c var, we need the distribution or the cumulative distribution function for a random variable. So, in this context, the random variable that you will consider is going to be the discounted gain on the asset. And then when you talk about the cumulative distribution function for that, we obviously need to then look at how it is going to be useful eventually in the paradigm of var. And since the definition of var involves something called quantile, we essentially looked at the definition of what is the upper quantile and what is the lower quantile, and illustrated it through a very simple example on discounted gain. And then we looked at four important properties of the upper quantile, and this was followed by a couple of lemmas. So, in one lemma, essentially that once you are given the distribution of the function, it gave you under certain condition how you can find the upper quantile as a inverse of the cumulative distribution function. And then we did another lemma which is actually even more important, where we talked about this random variable and then the function of this random variable, and we saw that how the upper quantile of the function of this random variable can be given as a function of the upper quantile of the random variable itself under certain conditions on the function f. So, in the next class we will continue this discussion and we will start off our narrative on value at risk. Thank you for watching.